Hello everyone, and welcome to Recitation with Sohail. Today we're going to solve problem 17 from section 2.2 of the 10th edition of Boyce and DiPrima. So the problem is the differential equation that we see in equation 1, that y prime is equal to 3x squared minus e to the x, all divided by 2y minus 5, with the initial condition y of 0 equals 1. And then after we find the solution to this differential equation, we want to find some interval containing 0 on which the solution is valid. So first, let's go ahead and solve this differential equation. We see that this is not a linear differential equation, which is unfortunate because that's a very well-studied class that we know how to solve. But it is the next best thing. It is a separable differential equation. That means we can separate variables, get all of the y's on one side, all of the x's on another side, and then we can just integrate each side independently. And from there, we can get our solution. So we go ahead and do that. All we have to do, in this case, is multiply both sides by 2y minus 5 to clear the denominator. So not too much work is needed to separate variables. And then even though the variables are separated in equation 0.2, I like to be very particular with the details and just go one step further. This isn't necessary, but I like to say that y prime is equal to dy over dx. So if I multiply both sides by dx, then I get equation 0.3. And now this is when I feel that the variables are really separated, because I can go ahead and write down my integrals and they have the dy on the left, the dx on the right. But again, this is just being a little nitpicky about details. You can go ahead and start integrating straight from equation 0.2 if you really want to. Nonetheless, once we get to our integrals, once we get to equation 0.4, we see that the antiderivative of 2y minus 5 is just y squared minus 5y. And the antiderivative of 3x squared minus e to the x is x cubed minus e to the x. Both of these are indefinite integrals, so there should be a constant of integration for each of them. But I just moved both of them to the right-hand side to just get one constant of integration, c. And then to solve for the constant of integration, we just use the initial condition that y of 0 is equal to 1. And we see that just by plugging in x is 0 and y is 1, c is equal to -3. So we can go ahead, plug that back into equation 0.5, and that's how we get equation 8. And in equation 8, we see that our answer is y squared minus 5y equals x cubed minus e to the x minus 3. Now, so far we have implicitly solved the differential equation, and oftentimes this is the solution. This is as far as you'll go. We just call this a solution because there's no derivatives in this equation. So this is a relationship that has to be satisfied by the x and y that satisfy our initial differential equation in 0.1. And it's just a simpler relation than the relation that we have in 0.1 because there is no derivatives. And that's why we consider it to be a solution, or the implicit solution. Now, thankfully, in this problem, we can actually go further. We don't have to stop at the implicit solution as we do in many other differential equations. In this problem, we can actually find the explicit solution. We can get y explicitly as a function of x. So to do that, we just have to treat this as a quadratic in y. So we take all of the terms with x, we move them to the other side. So we get 0 on the right-hand side. That's just a general technique for solving most equations. And now we see that this is a quadratic in the variable y. So it's 1 times y squared minus 5 times y. And then our constant term is e to the x plus 3 minus x cubed, which is not truly a constant, but we can treat it as a constant relative to y in order to apply the quadratic formula. So we can apply the quadratic formula because we have a y squared, a y, and then another term with no y's in it at all. So if we go ahead and apply our quadratic formula, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, then we can go ahead and simplify the algebra, and we should get that y is equal to 5 plus or minus the square root of 13 minus 4e to the x plus 4x cubed, all divided by 2. And now we see that we have two solutions here, the positive and the negative, and we just want to find one solution. And to do that, we just use the initial condition once again. We remember that y of 0 is equal to 1. And if we go ahead and plug that in, if we plug in x equals 0 into e to the x, we get 1, and into x cubed, we get 0. So 13 minus 4 times 1 plus 4 times 0. This part's just going to turn out to be 9. Square root of 9 is going to turn out to be 3. And we want 5 minus 3 over 2 to get us 1 in the initial condition. Whereas if we did 5 plus 3 over 2, we would have gotten 4. So the solution to the initial value problem is 5 minus the square root of 13 minus 4e to the x plus 4x cubed, all divided by 2. And that answers the first part of our question, which is to find a solution. Now, before we go on to the next part, finding the interval where it's defined, let's just recap on how we solved this problem. So, because it wasn't a linear equation, we checked for the next easiest class, which in my opinion is separable equations. And thankfully, we could separate the variables here. All we had to do was multiply by 2y minus 5, clear this denominator to the other side. Sometimes you will have to do more algebra to separate the variables, so this is a simpler example of a separable equation. But nonetheless, after we clear the denominators, we can replace our y prime by dy over dx and completely separate the variables. The key thing is to know when you've finished separating your variables, and that happens when all of the y's and the dy's are on the same side, and then the x's and the dx's are on the other side. So we don't want x times dy or y times dx to appear. If that appears, that means you haven't finished separating variables and you still have more work to do. But as we can see in equations 0.3 or 0.4, we only have a function of y with no x next to the dy, and then a function of x with no y next to the dx. So we have separated the variables. We go ahead and integrate, use our initial condition to get the constant of integration, and then we were lucky enough to see that this relationship can be viewed as a quadratic in y, which allowed us to use the quadratic formula to explicitly solve for y, which means that we didn't have to settle for the implicit solution as we oftentimes do. So now that we recapped and we have our solution to the initial value problem, let's go ahead and find some interval on which the solution is valid. So firstly, in order for the solution to be valid, it has to be defined. And we see that the only time our solution, which is in line 11, is not defined is when the discriminant is smaller than 0. So in order for the solution to be defined, the discriminant has to be bigger than or equal to 0. But that's not enough. There's more to do after that. So let's look back at the original equation. Not only does our solution y have to be defined, we need everything in equation point 1 to be defined as well. So we need y prime, the derivative of the solution, to be defined, and we need 2y minus 5 to not be equal to 0, so we don't divide by 0. Now, luckily, in this problem, those happen to be the same thing. If the derivative is defined, then it is equal to this quantity, so this quantity is defined, and we didn't divide by 0. Conversely, if we don't divide by 0, then the derivative is equal to this quantity. So it just so happens that in this problem, we only have to check one of those two conditions. But in other problems where the left-hand side is not just the derivative, where it's the derivative and some other functions, you might have to check both of them separately. So it's always good to keep both in mind. But in this case, we're just going to check that 2y minus 5 is not equal to 0. So we don't have to bother taking a derivative of our function. Just saves us a little bit of work. So our solution y, being what we have in equation 11, we see that 2y minus 5 is just going to be equal to negative square root of 13 minus 4e to the x plus 4x cubed. So this quantity will not be 0 if the discriminant, what I've highlighted in pink, is not 0. So all that means is we need the discriminant to be strictly bigger than 0 instead of bigger than or equal to 0. So we did actually get a small extra contribution to our restrictions on where the solution is defined by considering, or where the solution is valid, by considering not just where the solution is defined, but where it actually satisfies the differential equation. Now, what we would want to do, ideally, is to find all of the intervals on which this quantity is bigger than 0. And then we pick the interval that contains x equals 0 because our initial condition starts with x equals 0. So that would be the interval that we care about. Unfortunately, we can't explicitly solve this inequality by hand. We can't perfectly find the intervals for which this is larger than 0 working by hand. So we'll just settle for an approximation and just find some interval on which our solution is valid, as opposed to the largest interval on which our solution is valid. And then I should warn you guys, most differential equations courses that you take probably aren't going to ask you to go into as much detail as I'm doing to get this approximate solution. They might just give you an equation that you can solve exactly by hand, but I think it's interesting to see how this works once, just how you would get some interval. So I'm going to start with x equals 0, because we have to. That's what our initial condition was. Then I'm going to just guess some number that I think would work. So I'm going to guess that as long as x is between 0 and 1, then inequality 12 is satisfied. And I picked 1 just because it's easy to pick, and if I plug 1 into here, it looks like everything's satisfied, so I'm going to use that as my starting guess. Now, how do I show that this inequality is actually satisfied for every x between 0 and 1? Well, we start with our quantity, what we have in inequality, and I note that on the interval 0 to 1, I'm going to try to minimize 4x cubed. All right, so I'm over here, I'm adding 4x cubed. So I want to add the smallest thing possible to see how bad it can get, how small it can get. And that happens when x is 0. So in the worst case, I'm going to be adding 4 times 0. And then over here, I am subtracting 4e to the x. So I want to make 4e to the x as big as possible so that when I subtract it, overall, things become as small as possible so that we could continue to examine the worst case scenario. And e to the x is maximized when x is 1. So the worst case scenario is when I subtract 4e. And then just to keep doing this by hand, if you had a calculator, you could just plug it in at this point. But since I don't have one with me, I'm just going to say e is smaller than 3. So this worst case scenario is bounded by an even worse case scenario, which is 13 minus 4 times 3 instead of 4 times e. And that's just 1, which is bigger than 0. So in the worst case scenario, when x is between 0 and 1, this quantity is bigger than 1, and therefore it's positive. And we see that this 1 is not even the worst case scenario because we made some assumptions, right? We replaced the e with 3, and both of these worst case scenarios can't occur at the same time. The pink and the green occur separately, right? One of them occurs at x equals 0, and the other one occurs at x equals 1. So the achievable minimum, the achievable worst case scenario is not nearly this bad. But we didn't want to be exact, we just want something that works because it's hard to get the exact solution. And that's why we made all of these approximations. Because we're working by hand and we're just trying to make things as simple as they can be. So this is a half of an interval containing 0 on which our solution is valid. We got the right half of some interval. Now we just need to get the left half of some interval with 0. And when we put them together, we'll have an interval on which our solution is valid. So now I'm just going to guess -1. I'm going to guess that for any x between -1 and 0, the solution is valid. So just as before, we need to check that this is the case. Now, once again, I'm going to subtract the largest thing that I can possibly subtract. And when x is between -1 and 0, e to the x is maximized at x equals 0. So I will subtract 4 times e to the 0. And then I'm still adding 4x cubed. So I have to add the smallest thing I can add in order to get the worst case scenario. So when x is between -1 and 0, x equals -1 is going to minimize my x cubed to give me -4. So 4 times -1 cubed is -4. And altogether, this simplifies to be 5, which is certainly bigger than 0. So we again see that when x is between -1 and 0, we have that our discriminant is bigger than 5, which is positive. And just as before, this 5 is worse than the achievable minimum because the orange was minimized when x is 0, the blue was minimized when x is -1, but we were just playing it safe and taking the easy way out because we're working by hand. So in conclusion, if we put together both of these pieces, that the inequality holds when x is between -1 and 0, it also holds when x is between 0 and 1, then we see that the inequality holds when x is between -1 and 1. So -1 to 1 is a interval, or an interval, on which our solution is valid. It's not the largest interval, because as we saw, we had a lot of room for error in these approximations I made in 13 and 14. But it is a interval on which the solution holds, and that's all we want. So that's all I have for problem 17. And if you like the video, give it a like and subscribe.